Okay, so let's look at 2.3. This section is about solving first-order linear differential equations. So just recall a first-order differential equation that can be written in the form dy dx plus some function of x times y equals f of x, some other function of x here, is called a linear differential equation in the variable y. So we're going to learn how to solve differential equations of this form now. Okay, so let's look at a theorem now. Okay, so let's look at theorem 1. This theorem 1 is going to give us a procedure to solve first-order linear differential equations. So it says if you're given a first-order linear differential equation and you define your u of x to equal e to the integral of p of x dx, where p of x is this guy here, is the coefficient in front of the y, which is a function of x, then it's saying that u times y derivative equals f times u of x. So let's look at the proof of why this is true, then we'll look at an example how we can use this to solve first order linear differential equations. So let's look at the proof first. Okay, so proof. So the proof, we're going to use the product rule here. So we're going to look at this part. We're going to look at u times y derivative. So to do this derivative, we're going to have to use a product rule where the u of x will be the first function and the y will be the second function. We're assuming y is some function of x. So the product rule says it's going to be derivative of the first function times second plus first function times derivative of second. So let me write that here. Okay, so again, the u guy is what I'm calling my first function, the y is my second function, so it's going to be derivative of first function times second plus first function times derivative of second. But the derivative of y would just be dy dx. So again, if you call the first function f1, the second one f2, here's my product rule formula up here, f1 prime times f2 plus f1 times f2 prime. Okay, let's keep going. Okay, so next thing, so now u y derivative equals f times u implies, well, I can put this now in place of this guy here. So let's make that substitution. Okay, so I made the substitution, and I get this then, which I'm going to call star. Okay, now we're going to assume for a time being that u isn't 0, and then we're going to divide everything by u. Okay, so I'm going to write that here. Okay, so again, we're going to assume that u is not 0, and then we're going to divide both sides of star, so this guy here, by u of x, so divide u here, here, and here. So let's do that then here. So doing that, we get then, okay, so this implies then dividing everything by our u. So it'll be u prime over u here, y, and be u over u here, the cross off, so it'll just be dy dx here, and u will cross off there and just become fx here. And now we have this equation, and we have the original one up here. We're going to equate them now. Okay, so we now have, we have the original guy up here, which I've written here, and we have this guy here. I just put my dy dx first. So we have these two things must be true. They both equal f. They both have dy dx. So it looks like my p here would have to equal this. Okay, so let's state that. Okay, so again, this implies then p of x equals u prime over u. Alright, so I'm out of space now, so I'm going to erase a few things and continue with the proof. We're almost done with the proof. So let me just erase a few things up here. Okay, so here's where we left off. We showed that p equals u prime over u. So now we want to solve for u. and we basically want to show that u equals this. That's what the theorem's saying. So let's solve for u by integrating both sides. Let's integrate both sides here. So integrating both sides, we'll have integral of p of x dx equals integral of u prime over u dx. But this guy over here, since the derivative over the function is going to end up being an ln here. So let me write that. So it'll be ln of u of x plus c. Let's choose c to be 0. Okay, so choosing c to be 0. Then I want to get rid of the ln, so I'm going to exponentiate both sides with base e. So let's do that. So in that we have e to the integral of p x dx equals e raised to the ln of ux. Here the e and the ln will cancel here, so we'll just be left with u. So it'll be, basically we'll get this then. Alright, so we get then u equals e raised to the integral of px dx, which what we're trying to show here. So we've proven theorem 1, so hence claim follows. So hence claim follows, so we're done with the proof. So you put a little square at the end, means the proof's over. Okay, so now let's look at an example to see how we can use theorem 1 to solve these linear first order differential equations. Okay, so let's look at an example now. I'm going to erase this. We'll look at an example. Okay, so here's our example. Solve differential equation x squared y prime minus xy equals 2. We're going to show, we're going to apply theorem 1 to solve it. So first we're going to show that we can write it in this form. So dy, dx, and y prime mean the same thing. So we need to get the y prime here by itself, or like a 1 in front of it, I mean. So let's divide both sides by, divide everything by x squared here. So that's step 1, divide everything by x squared. Okay, so dividing both sides by x squared, we'll have this then. X squared is cancelled here, one of the x will cross up here, so let me write out which this will simplify to become. Okay, so now we can see that it's in the form of theorem 1. We have our y prime, and then we have our, so the coefficient, the function of x in front of the y is my p, so the negative 1 over x will be the p here, and this will be my f. So let me write that. Okay, so I've written the minus 1 over x as plus minus 1 over x like this. So the minus 1 over x will be the p, this guy here, and the f will be the 2 over x squared. Let's find our integrating factor, our u, now using this. Let me write it over here. Okay, so we'll have our u of x then equals e raised to the integral of 1 over x dx. I can pull a minus sign out in front here, and the integral of 1 over x is ln. So let me write that here. Then e will be negative ln of x. I guess that'll be a plus a constant, but I'm choosing the constant to be 0 here. Okay, so then I can bring that minus up on the x here, so it'll be ln of x to minus 1. Let me write that here. Okay, so it becomes e to the ln of x to the minus 1. These cancel, it just becomes x to the minus 1. So that's my u of x then, or integrating factor. We're now going to use this guy. Yeah, so now we're going to use this part here. So we're going to use u times y derivative equals f times u, where our u we found was x to the minus 1 and our f was the 2 over x squared. So making those substitutions over here, we get then, So we get this, we get x to the minus 1 y prime equals 2 over x squared. That's my f times my u. U is x to the minus 1, which you can write as 1 over x. Okay, so now our objective is to solve for y, so let's integrate both sides. So integrating both sides, we have then integral of x to the minus 1 y derivative dx equals integral of 2 over x cubed dx. But here we're integrating a derivative, so on this side the integral and the derivatives will cancel, so it'll just be x to the minus 1 y here. This we can write as, we can pull a 2 out and write this as x to the minus 3, so let me write it here. Okay, so we get this then. So I'm writing the x I'm writing as x to the minus 3 here. So integrating this, remember to integrate you just add 1 to the power, divide by a new power. So let me integrate this right over here. So we get then x to the minus 1 y equals 2x to the minus 3 plus 1 over minus 3 plus 1 plus some constant. So let's simplify this a bit here. This is minus 3 plus 1 is minus 2, and 2 over minus 2 be minus 1. So let's simplify this a bit here. So doing that we get then x to the minus 1 y equals negative x to the minus 2 plus c. We can then solve for y by multiplying both sides by x. So let's multiply both sides by x. Okay, so multiplying by x, we then this, and multiplying the x in, so we get then y. Y equals negative x to the minus 1 plus cx. So this should be our solution. Okay, so you can see now how we can use Theorem 1 to solve these linear first-order differential equations. Okay, so we're done with the section, so let's leave it there.